If you're wondering what happens to the electron shells, electron subshells, and electron orbitals when atoms form a molecule, we're not going to get into that. That's molecular orbits, and that's a bit beyond the scope of this series, to be honest with you. So we'll just avoid that. But what's the difference? But why? But what is an element? As opposed to what you might have heard of as bonding in compounds. An element is just a structure made of one type of atom or one type of element. So you can call an atom with a certain number of protons in it an element, like carbon is any atom with only 6 protons in its nucleus. You could equally call a substance that's just made of carbon atoms an element, like hydrogen gas is an element. It's just made of hydrogen. While a compound is something made of 2 or more types of atoms, like water, that's made of hydrogen and oxygen atoms, or carbon dioxide, that's made of carbon and silicon oxygen atoms even. Now, if we take a hydrogen atom, for example, so I'm drawing it like this for simplicity. In real life, as you know, electrons don't really orbit around the nucleus of an atom. It really just like sort of moves around in like kind of random directions, I guess. This wouldn't be stable in real life. What would happen is hydrogen would end up gaining an electron. If another electron came by, hydrogen would take it in and it would have 2 electrons orbiting it, and it then wouldn't have a charge of 0. It would have a charge of -1, because the +1 from the nucleus is outweighed by the -2 from the electrons, so you've got a net charge of -1. And then this would be attracted to an ion with a positive charge. This is one way hydrogen or any atom can become stable, by achieving a certain magic number of electrons around the nucleus, or even its valence shells even. And these magic numbers that you need in your valence shell, your outermost shell, are the same number as that of the valence shell of a noble gas. So in hydrogen's case, the nearest one, the easiest one for it to be like would be helium, which has 2 electrons in its valence shell. So He for helium. But why are the noble gases stable? When they're stable, in terms of electron configuration, they can't gain any more electrons, and it's very hard to remove an electron from their valence shell. But why is this? Well, this is actually to do with the attractive force an electron feels from the nucleus, and the repulsive force it feels from other electrons, if there are any other electrons orbiting the nucleus. So, let's draw hydrogen. So, here's a second electron trying to join hydrogen. It's experiencing an attractive force from the nucleus, but a repulsive force from the other electron that's already there. In this case, the attractive force is greater than the repulsive force, so a second electron can be added. However, if a third electron tries to join in, the repulsive force by the electrons is now greater than the attractive force by the nucleus. So this third electron will just bugger off. So and this is the same for helium. Even though you can increase the strength of the attractive force experienced by the electron by adding in protons. In helium, it's still not enough to add a third electron moving around it there. However, with lithium, which has got 3 protons in its nucleus, these 3 protons outweigh the repulsive force by the electrons, and so a third electron can join in. This effect of decreasing the strength of the nuclear charge an electron feels because of the counteracting repulsive forces from other electrons orbiting, or actually moving around the nucleus, not orbiting. It's called the shielding effect. And this is why electrons try to have a certain electron configuration, either by just merely gaining electrons, free electrons that aren't attached to any sort of atom, or by forming molecules. We'll go into an example of a molecule right the fudge now, bruh. So this is how a hydrogen molecule would form. You've got a hydrogen atom here with 1 electron moving around it. And we've got another hydrogen atom, same thing, nearby. What happens is, the nuclear charge will start to attract this electron, and the nuclear charge from this atom will attract this electron. So they're both feeling an attractive force from their original nucleus, and from this nearby new nucleus. What happens is, they both feel an equal attractive force from both nuclei. This is now pretty much one structure, called the hydrogen molecule again. Again, their electron shells, subshells, and orbitals sort of merge, kind of, into one molecular orbit, a thing called the molecular orbit. We measure the strength of a nuclei's attractive force to an electron by a thing called electronegativity. So, electronegativity. My spelling's terrible, so forgive me. So, strength of a nuclei's the charge of the nucleus, charge on an electron. Now, these 2 hydrogen atoms are now linked, so therefore there's a chemical bond between them, specifically a covalent bond. When they share their valences, they share their valence shells effectively. Their electronegativities are pretty much identical, because it's the same situation. It's 1 proton attracting both of them from either side. So yeah, it's a pure covalent bond. As opposed in compounds, when you could have 2 different elements in the molecule, or more than that, the molecule can be made of more than just 2 atoms. You could have the electrons pulled closer to one atom in the molecule, because its electronegativity is bigger, way bigger than the other atom or atoms in the molecule. And this has some weird effects that we'll go into next video, which is bonding in compounds. You can do things like give one side of the molecule a slightly negative charge and the other side a slightly positive charge. It can even give them full-on charges as opposed to partial charges, which is what I meant there. Yeah, so you'll see hydrogen nuclei stable not as hydrogen atoms, but as hydrogen molecules or hydrogen ions. Or even then, they'll be a part of some compound, right? Because an ion is now unstable by its charge, so it'll need to cancel out its own charge by connecting to another ion, a positive ion. When I get hydrogen gas, the smallest stable piece of hydrogen gas is the individual hydrogen molecule. In cases like this, the element is said to be diatomic, because its smallest, or most fundamental stable form is a structure made of two nuclei, hydrogen nuclei, or just two nuclei in general. When it's monatomic, its smallest stable piece is just one atom, one nuclei. This is the case for helium. And you might be thinking, I thought noble gases were stable, so they didn't need to share their electrons or anything. They don't. However, helium atoms are still bonded together in a very weak bond. Now think back to the second video in this series where I went on about the electron cloud. I don't know if I used that word, but an electron's sort of like, it's not really in a definite position in space, rather it's sort of in many positions at once, and it's sort of like cloud around the nucleus. So helium, this cloud here is all the positions you're likely to find an electron when you're not observing it in all these positions at once. This is where you'll find 90% of the time. Or electrons in that orbital, in that particular subshell, in that particular shell. This shape fluctuates, it changes very slightly. Parts of it will be denser at one moment in time, bits of it will be more dense. So, in one moment in time, this is for a very short period of time, so it's very thick here, it's like, you know, very dense here, and this is just a momentary fluctuation. And so we say that one side of the atom has a slight negative charge, the side where the electron cloud is thin, and we indicate that by putting a lowercase delta, which is this funny little thing here, and a plus, and this delta minus this side. The electron cloud is slightly thicker here. So in this moment, you're more likely to find the electrons over here than over here. There's a bigger range of positions you can be in here. But then we can see in the next moment, it can fluctuate another way. Delta minus, delta plus. So one side's slightly less dense, so the positive charges, you could say there's less negative charge shielding the nucleus, and so if an electron was to try and form a bond here, it would momentarily, because very briefly the attractive force from the nucleus on this thinner side is greater than the repulsive force by the electron cloud. And this is what keeps helium atoms together. or any monatomic substance together. So I'll give you an example. Electron cloud is thin here. This forms a temporary bond here, which is called a London dispersion force, or an LDF. And this slight positive charge here could attract the electron, move the electron cloud over here a little bit on the other atom as well. And let's say there's a helium atom here. This slightly denser part of this atom here, the slight negative charge can push the electron cloud away on this one, giving this atom here a slight positive charge, if I haven't messed up my explanation there. So another LDF there. And again, this is momentary, so all these will fluctuate, and other LDFs will form between different atoms, and yeah. LDFs are what we call a van der Waals force, because it's a force that can be experienced by any atom. It can happen to any atoms, and as you've guessed, this can happen to any atom really, because every atom has an electron cloud around it. Every nucleus has an electron cloud around it even, and it can fluctuate. But what happens is, in let's say a diatomic element like hydrogen, the covalent bonds are stronger than the LDFs. So these very weak forces won't disrupt the covalent bonds in any way in hydrogen. However, hydrogen molecules, or molecules in general, may be bonded to other molecules by LDFs. So I've got a hydrogen molecule here. Maybe an LDF here to this other hydrogen molecule. And so on and so on, and this will fluctuate. But within a hydrogen molecule, it's covalent bonds that are dominant, not LDFs. Oh yeah, I forgot to mention, with electronegativity, it's measured on a scale of 0.1 to 4.0. And an electronegativity difference of less than 0.5 is considered, that bond is considered to be a pure covalent bond. Now I'm going to talk to you about covalent networks. This is a covalent network. Usually in the molecule, there's a limit. You can have a certain number of nuclei in the molecule, because that's to achieve that magic electron configuration. Like hydrogen molecules, there's only 2 atoms in there. You couldn't have a third, 2 nuclei in there. You couldn't have a third one because of the shielding effect. With a covalent network, the molecule can be very, very large. So if we take carbon, for example, it can achieve this magic valency, a magic valency by either gaining 4 electrons or losing 4 electrons. In this case, it wants to gain 4 electrons. So a carbon atom will bind to 4 other carbon atoms. However, then its neighbour, or one of the carbons attached to it, will then bond to some other carbon atoms, and then one of its carbon atoms that is attached to it will bond to some more, and so on and so on, and it's like a grid of bonded carbon atoms. Examples of this are diamond. Diamond's just one big carbon molecule. It looks a bit rude actually, but that's a diamond. That's a covalent network. But another covalent network is graphite. Now I'm going to draw graphite here. So the carbon atoms can form a hexagonal ring, a 6-sided ring here, or a ring with 6 carbon atoms in it. So we've got a hexagonal ring here, one here, one here, and it'll keep on going on. So you get these sheets of carbon hexagons. So we're thinking, oh, graphite's very thin then. What happens is, these layer of carbon hexagons is bonded to another ring of carbon hexagons by LDFs. So we'll draw the electron cloud here. Draw some LDF forces between them. And that's all the thin side, so. Fun fact, graphene is the name for an individual layer of graphite. So, yeah. Now you might be thinking, okay, what happens in graphite is the electrons become what we call delocalized. What this means is they're not attracted to any particular nuclei, so they just drift around all the nuclei. And LDFs happen, and you've got yourself a graphite there. That's a bit of a butchered explanation, but that's pretty much the main idea. And we consider the element carbon. It can exist in many forms. One form is clearly diamond, one form is clearly graphite. These are allotropes of carbon. That's the technical term for it there. Lastly, let's look at metallic bonds. Covalent bonds tend to occur in non-metals. Metallic bonds tend to occur in metals. So let's say you're lithium, and I'm only going to draw its outermost electron layer. Now you can either gain 7 electrons to get the electron configuration of neon, the noble gas, or lose this one to have the electron configuration of helium. So let's say you're near another lithium atom, or a bunch of lithium atoms. The electrons become delocalized, so they're not attracted to any particular lithium atom. Because remember, electrons are actually a cloud around the nuclei, around the nucleus. And so, while the attractive force the electron experiences is enough to make it move around the nucleus, it's still fairly weak. The electron shell between the outer one and the nucleus in lithium is still enough to make that very weak. So this electron can drift over here, but the attractive force isn't too strong here in any of these, so the electrons just drift around. And what you end up getting is, get this, you get a bunch of lithium ions with electrons moving around them. So they sort of exist as this big, huge, let's fix my camera, sort of molecule, really. It's called a metallic bond, where the nuclei is attracted to this sort of sea of electrons, or sort of field of electrons that moves between each nuclei there. This can, of course, occur in compounds as well. But there you go, we've done it at last. It's been a while since we uploaded a chemistry video, but that's that. Join me next time when we'll be discussing bonding in elements. See you then.